Let's say when we have two materials, right, that are reacting to form a product, so our main aim will be to produce more of that product in the system by minimizing the cost and by fully utilizing all of our reactants. So in this case here, let's say A is a very expensive raw material that we have, and in a normal operation, A has a very low conversion, right? The X is very low, the conversion is very low. So if let's say we have 1 mole of A, it might only react, and we might have still some leftovers of A unreacted, okay, B unreacted, and we only form about 0.5 C. So we aim, if possible, we can increase the production of C, reduce the amount of A that is left as waste in our process stream. So one way to go about with this is by pushing the reaction forward, where with the amount of A and A that we have, we can put excess of B, where we are able to produce more C, use up almost all of A, and with some B left in the system. So when this happens, then we are able to increase the production of C because A is all used up. Why do we do this? It's because we don't want to lose our money because of the unspent A, right? But when we have B in excess, then there are other implications to our process. For example, we need a bigger equipment, right? We need a big storage. We might also need maybe a bigger compressor to compress and send B into the system. Okay, we will have a much, maybe more equipment that will be used throughout the process. But more importantly, A is used up, and the reaction that we have here, okay, the reaction that we have produced the product that we want, right? It produced the product that we want, and this C is the desired product. It is not a product because of a competing reaction. So that is the reason why we introduce excess into the reaction, and in particular, it's for combustion, we usually introduce excess air. So what is excess air? How do we go about calculating an excess air, and why is excess air is important? Okay. Let's say here, what we have is a reaction of butane. Okay, we have butane that is reacting with oxygen, right? It reacts with oxygen. It forms carbon dioxide and water, right? When it forms carbon dioxide, we know this is a complete combustion. Theoretical air is only for complete combustions, and complete combustion is identified by formation of carbon dioxide. If there is carbon monoxide formed, then this is not a complete combustion, right? This is a partial combustion. So a partial combustion, it does not gives you your theoretical air, right? It doesn't give you the theoretical air. Only complete combustion will provide you the theoretical air needed by the reaction to take place, because it will tell us what is the theoretical oxygen required for the reaction to happen. Okay, so we have a stoichiometric reactions for this particular reaction. Are they balanced? Let's look whether it is balanced or not. We have 4 carbon. We have 4 carbon. So we have 4 carbon there. We have 10 hydrogen. So we have 10 hydrogen. And we have 4, 8, and 5. So we have 13. So each 13/2 for oxygen. So we have 6.5 mole of oxygen that is reacting with 1 mole of butane to produce 4 mole of carbon dioxide and 5 mole of water. Okay, so we have the reaction. It's a complete combustion and it is balanced. Now we want to calculate the number of theoretical moles of oxygen, right? We want to know how many moles of oxygen for the given mole of fuel. So what is the mole of fuel that is given? We are given 100 mole of butane. All right, we are given 100 mole of butane. So we know 1 mole of butane of C4, it will react with 6.5 mole of O2. Okay, so now we have 100 mole per hour of C4, it will react with will be 6.5 times 100, that will be 650 mole of O2. That is the amount of oxygen that is required for the reaction combustion to take place so that it can occur as a complete combustion. All right, so that one is taken care of. We have 650 mole per hour of oxygen. All right, now we want to know what is the theoretical mole of air, right? We know that that is the number of moles of oxygen that we require. So, okay, so from our previous exercise, we know that in 1 mole of air, okay, 1 mole of air, we have 0.21 mole of oxygen. Therefore, for 650 mole of oxygen, we will have, okay, let's do the calculation here a little bit. So it will be 650 mole of O2 times 1 mole of air, 1 mole of air divided by 0.21 mole of O2. Okay, so we are getting about 3094 mole of air. So our value will be 3094 mole per hour of air as our theoretical values. Right? Theoretical air will be 3094 mole per hour of air. Okay, remember how do we calculate the theoretical of air? It's all based on the theoretical oxygen that is required based on your stoichiometric information for a complete combustion only. Okay, it's for a complete combustion only. Okay, let us now look at the percent of excess air that is required to make sure that the combustion reaction goes into a complete reaction. So let's go to this checklist one by one to see what does it mean by a percent of excess air. So we know that we have to base on the balanced stoichiometric reaction first. So we have our balanced stoichiometric reaction here, where we have CO2 produced in the system. So it is a balanced reaction And it is a complete combustion because you have a CO2 that is produced in the system. We already calculated the number of theoretical mole of oxygen required, which is for 1 mole of butane, you will require 6.5 mole of O2. So for 100 mole of butane, we required 650 mole per hour of O2. Okay, that is the values that we had calculated previously. And then we also calculated the theoretical moles of air from the number of oxygen that we require. So the values that we already calculated was 3094 mole per hour of air. This is the theoretical oxygen, O2, and this is our theoretical air. So let us check what is the amount of air that is fed into the system to see whether we are feeding the excess values or we are not. All right, let us see the first one. We are providing the system with 3000 mole per hour of air. So we can see that our theoretical value was 3094. So this one here is a little bit short, right? This is less than 3094. So this is not in excess, all right? The first one is not in excess, so we need to pump in a little bit more so that we are able to have this complete combustion reaction. Else, we might not have a complete combustion reaction. It might lead to another reaction because this means 3000 mole per hour is in excess for a different reaction. Okay, because the mole ratio is not achieved yet. Okay, let us look into the second one. When we feed in 5000 mole per hour of air, is this greater than 3094? Yes, it is greater than 3094. Let us calculate what is a percentage of air, excess air that is provided. So we know that to calculate the percentage of excess, so it is just a mole that we have theoretically, it is the mole that we feed in minus the mole that is based on the theoretical value for air divided by the theoretical value times 100%. So we will have 61.6%. So we can say that for this particular system, when you supply about 5000 mole per hour of air into the system, we are supplying the system with 61.6% excess air. Okay, what can we say from this exercise? It tells us that to calculate a percent of excess air, you don't need to know how much O2 had been spent. You only need to know what is the value of the theoretical air required and how much air is being supplied into the system. All right. There are only two things that you have to know. What is the values for the theoretical air and what are the values that are being supplied. Okay, some take-home notes before I end the combustion section. When you are actually drawing your flow chart, remember if you are using air, okay, if you are using air, always have N2 as an unburned material that's coming out in the product stream. There are also unreacted O2 and also unreacted fuel if it says that none of those are being used up. Okay, in your product stream, you will also have your product that are produced. Either it is a partial, a complete, or can be both. Okay, you will have H2O produced, CO2, and also CO. And if there are information on excess air and oxygen, please use them carefully. Okay, how you are actually accounting for them. For example, when excess air is given as 30% excess, then your feed value will be equals to 1.3. Okay, 1.3 times the number of moles of your theoretical. So that will give you the amount of feed that is supplied into the system with excess.